Hello, my name is Connor Stone, and today I'm going to talk to you about the AutoProf software, which converts galaxy images into reduced non-parametric surface brightness profiles. I'm going to explain a little bit about how the algorithms work and how it compares or what advantages it has to other photometry softwares. Now, we got to talk a little bit about the ultimate goal of the AutoProf code. See, what we wanted to do was create a package which could very quickly get people from data to results. So it can actually work directly from an image of a galaxy. In this case, we have a really good example where there's a single galaxy that's the dominant object in the image. There's lots of space around it that gives us a good handle on what the sky value is. And there are no bright overlapping objects. There's still plenty of other smaller objects in the view which could potentially disrupt a photometry software, but AutoProf is intended to deal with this sort of thing. Now, it goes straight from an image like this to the surface brightness profile, which is the brightness of the galaxy as a function of radius or semi-major axis out from the center. And of course, it tries to go as deep as it can. So this is what we want AutoProf to be able to do. Before we can extract a surface brightness profile, because AutoProf is intended to work straight from an image, it needs to learn a little bit about that image before it can go any further. The first step is a bit of pre-processing. You can see these cyan and red circles around the image. These are identified point source objects where the cyan ones are identified as likely stars. AutoProf uses these in order to compute a PSF for the image. Now, the PSF doesn't need to be extremely precise. AutoProf mostly uses that to set a physical scale on the image where we expect information to be available, below which is really just pixels. AutoProf also takes a band of pixels around the image and uses these to construct a histogram that it can then use to get a good measure of the sky level. For both the PSF, the sky level, and really anything about AutoProf, you can override the parameters with your own values if you like, if you have more advanced algorithms in order to compute these. But AutoProf includes out of the box the ability to handle this stuff for you so you can get right to your science. Now, AutoProf requires that the galaxy is roughly centered in the image, or that you give it roughly approximate center coordinates, but they don't need to be precise. So AutoProf is able to find a more precise center by itself for a galaxy. In this case, I have actually intentionally moved the starting point way away from the center of the galaxy so we can see how it progresses towards the center. You can see in this first panel here, what AutoProf does is it takes a ring of surface brightness values from the pixels, computes an FFT, and uses the first mode of the FFT in order to compute a phase or direction of increasing light. It'll do this for a number of rings and then take the average direction of increasing light, which is relatively robust to any sort of point sources or other objects which may cause the centering to get confused. So it heads towards the global brightness peak for that galaxy until it gets near the center. Finally, for the last step, it assumes a 2D parabola and tries to fit at the subpixel level in order to get right in at the exact center. So once it's found the brightness peak, it's found the background sky level for the image and the PSF, it's ready to start learning a little bit about the galaxy. So to begin with, AutoProf, like any other galaxy fitting code, needs initial parameters to begin with. You can supply these, of course, but since AutoProf is intended to work automatically out of the box right from an image, it will actually compute its own initialization for any galaxy. The way that it does this is first by computing the position angle of the galaxy. it takes rings of geometrically increasing size until it gets close to the noise level of the image. And then it will use the second FFT mode in order to compute a phase along each of these circles. Taking the average value gives you a global position angle for a galaxy. Once you know the position angle of the galaxy, or at least a rough global estimate of that, you can then compute the ellipticity for the galaxy. So AutoProf will sample a variety of ellipticities until it finds one that is a reasonable match for that galaxy. It's important that it samples all of these instead of just starting at a random point and optimizing, because there can be local minima along the way. In this case, the global minima is out here, but there is another local minima in near the center because this galaxy happens to have a bar which would align with that very narrow ellipticity. Now that we have a starting point for the galaxy, we can optimize individual isophotes. You can see here, each one of these isophotes has been fit to the image. They are, again, geometrically increasing in size. This efficiently represents the structure of the galaxy. And you can see that there's a lot of structure found here in the center. AutoProf is able to match that structure. And the way that it does it is by minimizing this function here. The core thing that AutoProf is trying to minimize is the second Fourier mode. So along a given isophote, we sample the pixels, and then we compute an FFT and take the power in the second Fourier mode. We then randomly perturb the parameters until we can find a minimum in the second Fourier mode, but there's a little bit of regularization included, just a sprinkle of machine learning in order to make the fits more robust. So what this term represents with all of these components here is a penalization for being very different from your neighboring isophotes. So the isophote's ellipticity minus the ellipticity of the neighboring isophote is used here, one less and one above, and same for the position angle. So this forces AutoProf to try and find isophotes with relatively similar ellipticities and position angles for adjacent isophotes, but it still gives complete flexibility if that happens to be the ideal fit. So you can see here that AutoProf does indeed fit a lot of different ellipticities and position angles for the isophotes, but it doesn't get overridden by features such as this bright point here and this bright point here, which, since they run almost straight through the center of that galaxy, can actually cause isophotes to sort of collapse into very low ellipticity pointed along the line between those two stars. AutoProf is able to overcome that by using a bit of regularization to tell it to avoid cases where a single isophote collapses. Now that the isophotes have been fit, I can extract a surface brightness profile. AutoProf does this by subsampling or interpolating the phase profile, is what I call it. That's what we determined before. It would be a profile of ellipticity and position angle for this galaxy. I then interpolate that so I can get more isophotes, more information about this galaxy. And then along each isophote, I sample the pixels and take a median, although you can use a mean if you like, or a mode. AutoProf has plenty of options to customize exactly what you want to do. You can also use sigma clipping. All of these are built in, and AutoProf is flexible enough to let you adjust these if you need special considerations for your image. Similarly, you can mask an image. AutoProf will sample the flux around an isophote, take the median, and that gives you the average brightness for a given semi-major axis. Now, AutoProf employs an extra trick in order to dig about 10 times fainter into an image, and that's called band averaging, or that's what I call band averaging. You can see that right here, the error was about to tick up, so the band averaging initiated, and the errors drop back down for a little while until we get deeper into the image. What the band averaging does is, instead of just sampling the pixels that land on an isophote, it actually samples a band of pixels and takes the average of all of those pixels within a band. I've exaggerated it here in this image. Mostly what it means is that AutoProf is taking advantage of the pixels in between the isophotes that you see on the image here. So they're so close, at least when we're further out in the image, they're so close to each other that they may as well be used for the same isophote, and we find that it increases the sensitivity by a factor of nearly 10. So AutoProf is able to reach a lot deeper that way. You can customize all of this if you want and turn it off entirely, but this does actually significantly increase the signal that AutoProf has to work with. You can also see that some of the isophotes here are dashed instead of solid. And the reason these ones are dashed is because they are extrapolated. AutoProf only fit out to the solid lines. And then what I do is I take the ellipticity and position angle and just fix those and extend further out. So long as the structure doesn't change dramatically for the galaxy in the outskirts, this lets you get a lot further out than you would easily be able to fit, because noise, interloper objects, stars, they would all be much stronger in the fit than the signal itself, which is similar to the sky level at that point. You can actually see on the image here, this horizontal line is the noise in a single pixel, the sky noise in a single pixel, and you can see AutoProf is able to drive considerably deeper using these techniques. So, is that the end? We've got our surface brightness profile. Well, not quite, because now that AutoProf has a deep understanding of this galaxy, we can actually go further. We can learn even more about it using our initial information about its structure. So, now that we know the position angle of the galaxy, we can create radial profiles that are aligned with the semi-major and semi-minor axes. Then, using these radial wedges, we can extract a surface brightness profile just within that wedge. That allows us to get a number of surface brightness profiles which collectively tell us a lot about the structure of that galaxy. And in fact, this is extremely customizable. You can change the angle relative to the position angle. You can change the number of radial profiles you want, so you can sample the entire galaxy. If you wanted to do, say, 20 radial profiles all the way around, you can do that. And AutoProf will handle all of the angles, the widths, and all of that for you, so you can start to learn about the structure of your galaxy. Now, we also have a phase profile of position angle and ellipticity, and surface brightnesses, which means we have all the information we need to construct a galaxy model, or at least an axisymmetric galaxy model. So this image here is entirely artificial. It's created from the surface brightness profile, and it essentially encodes all of the axisymmetric structure of the galaxy, which you can even see some of the spiral arms represented in here. Now, when we subtract these two, what we get is a residual profile that shows us all of the non-axisymmetric structure of the galaxy, and in fact, detailed structure all the way into the center, which can be really useful. There are actually a whole bunch of similar tools in AutoProf, and I'm not going to go into all of them, but chances are that if you have a science question about your galaxy, you can answer it with one of these tools, or create your own and stick it into AutoProf very easily, just as a plugin. So AutoProf is actually, at its core, more a pipeline algorithm than a photometry algorithm. You can actually add in whatever other code you want, rearrange the various components of AutoProf, and even have decisions along the way. For example, you can decide if a galaxy is an edge-on galaxy and run different analysis depending on whether or not it's edge-on. You can also test whether or not if it failed, and then go back to the beginning after adjusting some parameters until you finally get a point where you're confident in the fit to that galaxy, and then you can write the profile out at the end. These will help you in analyzing more details about your galaxy. Another important feature in any software project is the documentation. So AutoProf has extensive documentation for all of the different features that it has available. It also includes examples on the galaxy that I've been using through this presentation. It includes examples of different configuration files to do all of the analysis that I've discussed on that galaxy, so you can see from a starting point how it's done. All right, now we also, in the AutoProf paper, compared AutoProf with a variety of other photometry softwares, including PHOTUTILS, XVISTA, and GALFIT. There are a whole bunch of other codes out there for doing similar analyses, but these three let us really test how AutoProf fits in the space of photometry codes. One of the main results was that while AutoProf, XVISTA, GALFIT all agree with each other in the central parts of galaxies to a really consistent precision, when we get out to the outskirts, there are some significant differences. Because of the techniques that I discussed earlier that AutoProf employs, it's able to reach deeper magnitudes. What we're seeing here on the x-axis is the deepest isophote that AutoProf reached before hitting a certain error threshold. So you can see a lot of them made it to 2930 mags per arc second squared. And we compare that with the deepest isophote that PHOTUTILS got to before it reached a certain error threshold. And you can see the median depth that AutoProf reaches in comparison to PHOTUTILS is about 2.8 megs per arc second squared, or a little over a factor of 10 deeper. Sometimes it goes considerably deeper, something like 8 or even 10 megs per arc second deeper. In those cases, the band averaging isn't quite that good. What's really happening here is that PHOTUTILS has reached a stopping condition, perhaps a bright star, that AutoProf was able to overcome. Because of the regularization that AutoProf employs, it's able to remain stable even while it's fitting through a relatively bright star that other algorithms may get distracted by. So AutoProf can march on and collect the full information for that galaxy. Of course, because it uses the median around an isophote, it will, for the most part, ignore a star once the fit is properly aligned. Here we see the same comparison, except now it's between AutoProf and XVISTA. And AutoProf is able to reach a median depth of about 1.97 megs per arc second squared deeper, which is not quite a factor of 10, but still considerably deeper. And you can see that there are some cases where AutoProf is able to reach considerably deeper, again, because it's able to more stably pass through bright objects. Now, this was a bit surprising because XVISTA is a human-in-the-loop algorithm, but still it seems that there were some cases it wasn't able to go all the way to the edges. Finally, we've got the points of greatest disagreement in inclination. So what we're showing here, this row at the top here, is an image of an example galaxy where AutoProf and one of the other algorithms had a large disagreement in the inclination for that galaxy. Each column is a different galaxy, and you can see all of the different fits for that galaxy. AutoProf on the second row, then PHOTUTILS, then XVISTA, and GALFIT. A blank space is where the code wasn't able to recover an image of that galaxy. So, for example, here, VCC 2070, AutoProf was able to get a relatively stable solution quite far into the outskirts for that galaxy at an inclination of 42.5 degrees. But PHOTUTILS had a significant disagreement with AutoProf because of this isophote here. You can see that that isophote lands on two kind of bright stars, and that's what I discussed earlier, an example of a situation where two stars are somewhat aligned with the center of the galaxy, and that can cause an isophote to get thrown off unless you're using the stabilization techniques that AutoProf employs. XVISTA, because it has a human in the loop, was able to, the human was able to tell it that one isophote is no good, just go with the other ones, and it was able to also get a stable solution. In this case, GALFIT focused more on the center of the galaxy than the whole thing. People who are better with GALFIT may have been able to get the whole thing to work, but I was trying to employ all of these except XVISTA in an automated context. There's a similar story for each one of these galaxies. The first three are large disagreements with PHOTUTILS, the second three are large disagreements with XVISTA, and the final three are large disagreements with GALFIT. For the most part, when there's a disagreement with GALFIT, it's because GALFIT focused on a feature in the center of the galaxy and not the whole galaxy, and that's in part because GALFIT was only allowed to use at most 2 Sérsics in order to fit the image, whereas AutoProf and the other algorithms are non-parametric. They can represent the full structure, no matter how complicated it is for that galaxy. All right, so in summary, AutoProf is a complete fitting package. You can give it an image, and you need a 0 point for the photometry, and it will do all of the pre-processing and analysis steps it needs in order to give you a surface brightness profile. This can be done by just about anyone very easily right from the FITS file itself. Now, if you want to dig deeper for a galaxy or a population of galaxies, you can use some of the advanced tools in order to construct a more detailed analysis pipeline, employing whatever algorithms you want to use, and a lot of algorithms that are already built into AutoProf. If you compare AutoProf with similar algorithms, because of these techniques that it employs, like the band averaging and the extension of the isophotes, it's able to reach roughly a factor of 10 deeper in its deepest isophote for a given galaxy, which I think is pretty good. So that's a quick overview of AutoProf. If you have any questions, you can always consult the paper, the documentation, the GitHub, and you can email me. I'm always happy to answer questions and talk about how we can extend AutoProf to make it more useful for more people. That's all from me. Thank you. Bye.